Welcome to the deep dive. Today we're talking about what might just be the most uh, complex and aggressive digital pet ever made.
That's a great way to put it.
Imagine a little device, it's smaller than your palm, and it runs on a really low-cost computer, a Raspberry Pi Zero W. It even has a little e-ink screen that shows you its mood. And this pet, it gets happy when it eats Wi-Fi passwords. Its entire reason for being is to teach itself how to be the best, most efficient wireless network auditor it can possibly be.
And that little creature is the Pwnagotchi. It's an open source project, and it is, frankly, brilliant in how it packages these really advanced cybersecurity concepts into something that feels, well, alive.
Right. And today we're going far beyond just the cute visuals. This is a deep dive into its algorithmic core. We're going to unpack how the system uses deep reinforcement learning, or DRL.
Yep, DRL, to basically automate and optimize the entire process of wireless network reconnaissance. Specifically, it's hunting for those WPA and WPA2 four-way handshakes.
So our mission today is to really get a handle on the conceptual shift this thing represents. Because if you think back to the early days of, wireless auditing, you had manual stuff like war driving.
Oh, yeah, literally driving around with a laptop and a big antenna on your car.
Exactly, hoping you'd stumble across a vulnerable network. It was slow, it was passive. But now we've jumped to this dynamic, algorithmically driven, adaptive agent. So why was that jump necessary?
Well, because the 802.11 attack surface has just exploded. I mean, we're not talking about a few home routers anymore.
No.
We're talking about massive enterprise environments, dense cities, huge industrial control systems, and literally billions of new IoT devices. They're all broadcasting wireless signals.
And a static pre-programmed script just can't handle that.
It can't keep up. It's too dynamic. You need an agent that can see what's happening, assess the situation, and then optimize its own behavior in real time. The intelligence has to be in the machine itself.
And the really wild part is how accessible this all is. You're not talking about some million-dollar defense contractor's lab equipment.
Not at all.
You're talking about parts you can buy for, what, under 50 bucks?
Exactly. And that's the democratization factor. Pwnagotchi takes these incredibly sophisticated DRL concepts, these are the same ideas that are driving advanced robotics, complex logistics, and it marries them to cheap, off-the-shelf hardware.
So it just completely lowers the bar.
It completely lowers the barrier to entry for anyone who wants to do this kind of dynamic adversarial testing. And that forces everyone, from a home user all the way up to an enterprise security team, to really confront how easily an advanced, constantly optimizing auditor can be deployed against them.
So this little thing, it's not a gimmick. At its heart, it's a fully operational cyber-physical system, a CPS.
It absolutely is. And thinking of it as a CPS is, I think, the key to understanding it. The agent's internal brain, its computational model, is directly and constantly being informed by the physical world around it.
Meaning the Wi-Fi signals in the air.
Right. The 802.11 spectrum, things like channel load, how many access points it can see, the received signal strength indicator, the RSSI, all of that is continuous real-time input. The little e-ink screen just shows you the result of that complex learning process.
So if it's doing well, it's happy.
If the agent achieves a high internal reward state, its mood is happy. If it's been trying for a while and getting nowhere, it looks sad or bored.
That's such a brilliant piece of human-computer interaction.
Yeah.
You're linking this really complex mathematical outcome to just a simple intuitive emotion.
Yeah.
But that foundational hardware, the little Pi Zero W, that dictates everything, doesn't it?
It dictates all the constraints.
Yep.
Yeah. This is a very resource-constrained platform. We're talking a single-core CPU, 1 gigahertz, and a tiny amount of RAM.
So everything has to be lightweight.
The machine learning algorithms have to be incredibly lightweight, and every single input-output operation, every I/O call, has to be scrutinized and optimized. That constraint, kind of paradoxically, is what defines the entire engineering challenge of the project.
Okay, let's unpack this then. Let's get technical. If this agent is continuously learning, what's the actual, step-by-step pipeline? How does it turn passive wireless noise into an active, intelligent decision?
We can break it down into a continuous closed-loop system, a loop that has 5 distinct stages, and this whole loop just repeats itself hundreds and hundreds of times a minute as it's monitoring the airwaves.
Okay, so let's start with its senses. How does it perceive the world?
That's stage 1, perception, or just sniffing. The system puts its Wi-Fi card into monitor mode. This lets it capture all 802.11 traffic. It doesn't matter who it's addressed to. This raw stream of data beacons, probes, all the management frames, that's its eyes and ears. It's constantly updating its picture of the environment.
And then all that raw data has to be turned into some kind of knowledge, stage 2.
Which brings us to stage 2, cognition. This is the reinforcement learning update. The agent looks at the current state of the world, which we call S, and it's basically a vector, a list of numbers summarizing the environment. Then it updates its internal guess about the value of different actions. That's the Q value function.
And that update is based on whether its last action was successful or not.
It's driven mathematically by the reward R that it got from the last action it took.
So once it sort of knows the value of its potential moves,
Yeah.
it has to pick one.
That's stage 3, action selection. And this is governed by what's called the policy. The policy, pi of S, is essentially the agent's strategy map. It's what it's learned over time. Based on the current state, SS, the policy tells it the best action, A, to take to maximize its future reward.
And that could be just waiting, or it could be actively doing something.
It might be waiting, or it might be forcing a disconnection.
And if the policy does decide to attack, that's when it leaves the purely mathematical world and actually touches the physical network.
Precisely. That's stage 4, intervention, or packet injection. This is the execution phase. The agent uses specialized tools to perform that action it chose, which more often than not means injecting specially crafted packets like a authentication packet into the network to trigger a very specific response.
And then stage 5 is bagging the prize.
Stage 5, archival.pcape. The captured handshakes, which are the whole point, they get stored in PCAPI files along with other important data like GPS location or signal strength. And then that's saved for later, for the really resource-intensive offline cracking. The key is that this isn't a script. It's a loop that learns, allowing it to adapt its strategy over time to get the most reward.
Okay, now let's zoom in on something that I found really genuinely surprising about this design. The critical system bottleneck. It's not a flaw in the Wi-Fi protocol. It's not in the DRL algorithm itself. It's a limitation that's baked into the cheap hardware.
This is the Achilles heel of the original Pwnagotchi.
Absolutely. The system's overall efficiency, its speed, isn't limited by how fast the algorithm could theoretically run. It's limited by the systemic inefficiency of just moving data around inside that low-cost hardware.
Okay, explain that. This I/O latency problem. Why can't the reinforcement learning core just get fresh data instantly?
Well, the AI core, to make good decisions, needs near instantaneous, up-to-the-second information about the network to define its current state, that S vector. But Pwnagotchi relies on these external kind of legacy Linux tools.
The air cracking suite.
Primarily the air cracking suite, and specifically it has to parse the real-time CSV or text output that's generated by arrow dumping.
So the Python script that's running the AI and the C program that's monitoring the network are two totally separate things.
Completely separate processes. And because they're not designed to talk to each other using modern low-latency methods like, say, shared memory or direct API, they have to communicate using the slowest possible method, which...
File I/O, writing to the SD card. The arrow dumping process writes its data, the list of networks, their signal strength, and so on to a file. Then the Python RL script has to stop what it's doing, open that file, read it, parse all the plain text, and then convert it into that state vector S.
On a powerful machine, reading a file might take milliseconds. On a little Pi 0W.
It's significantly longer, it's much more resource intensive. The Pi 0W has a relatively slow internal I/O bus, and your typical cheap SD card has notoriously high read-write latency. So this whole operation just eats up precious CPU cycles, but more importantly, it completely compromises the freshness of the state data.
The data is stale by the time the AI sees it.
It is. The agent is constantly making decisions based on data that might be several seconds old, or in some cases even tens of seconds old.
So it's like the agent is trying to command a battle, but it's getting its battlefield reports delivered by a very slow messenger on foot.
That's a perfect analogy. And the consequence of that is what you see as inconsistent monitoring, or people complaining that their agent gets stuck. If the AI decides to switch channels because the state file said there was congestion, but the network actually cleared up 10 seconds ago.
It's made a wasteful move.
It's made a delayed, suboptimal, and totally wasteful move. And that severely impacts the agent's ability to learn a truly optimal, real-time strategy. The future of these agents really depends on bypassing that file I/O bottleneck entirely.
Okay, let's set aside the hardware's sluggishness for a minute and really dig into the mathematical genius underneath it all. This is where the agent's brain actually thinks, and it's all framed within this concept of the Markov decision process, the MDP.
Right. The MDP is the essential theoretical model that lets us apply reinforcement learning in the first place. It dictates how the agent views its world. Formally, an MDP is defined by a tuple, a set of 5 things, S, A, P, R, and gamma.
And those stand for state, action, probability, reward, and
The discount factor. And the entire goal, the whole point of the exercise, is for the agent to find the optimal policy, the best strategy that maximizes the total amount of reward it can get over time. For Pwnagotchi, that just means the total count of valid, unique handshakes it captures.
Let's focus on that state space S. This is the agent's reality. What kinds of complex variables are you packing into that S vector?
S has to contain everything that's relevant for making a good decision. So that includes external environmental things like how many networks are visible right now, what's the channel load, is the frequency busy, the average signal strength for the networks it's targeting.
Well, also internal things, right?
And also critical internal metrics, things like the agent's current mood, which is really just a number quantifying its recent success, and very importantly, the stagnation counter.
You mentioned before that a key technical hurdle here is that a lot of these wireless variables, like signal strength, are continuous numbers, but this simple Q-learning model, it needs discrete states. It needs buckets.
Yes, that's a huge challenge. Q-learning works by building what is basically a giant lookup table. Every unique state, S, is mapped to the value of every possible action, A, but you can't use a continuous variable, like an RSSI that can be anything from -10 down to -95. You can't use that as an index in a table.
So you have to simplify it.
You have to perform aggressive discretization. You have to chop it up into bins.
Can you give us a concrete example of how that works?
Sure. Let's say the signal strength reading is -65 dBm. That's a continuous value. For the agent to use it, we have to map it to a finite category. So we might define a rule. If RSSI is better than -50 dBm, call it state 1, excellent target.
Okay.
If it's between -50 and -75, call it state 2, good target. The challenge is that you lose fidelity. You lose all the nuance within that 25 dBm range. So if the signal drops from -74 to -76, the state suddenly flips, which can sometimes make the learning process a bit unstable.
Too few states and your policy is too crude, too many, and the pi zero just runs out of memory.
Exactly. It's a trade-off.
And then there's this almost philosophical challenge of the Markov property. We agreed that for reconnaissance, the agent's history, what's happened in the past, really matters.
It does. The strict Markov property says that the future depends only on the present. But if an agent keeps looking at a network that never, ever gives up a handshake, it needs to remember that prolonged failure. The history of that failure is important information.
So Pwnagotchi has to kind of cheat the Markov rule.
It violates the strict requirement by augmenting the state S with a sense of history.
And that's where the stagnation counter comes in. It's a form of short-term memory.
That's it, exactly. The stagnation counter just tracks how long the agent has been stuck in a low-reward state, just fruitlessly monitoring or attacking the same thing. This time-based metric is then included as a discrete part of S. If that counter gets too high, the agent transitions to a new penalized state, and that forces its policy to choose an exploratory action, like jumping to a new channel, even if the signal strength right now looks good. It's a necessary hack to keep it from getting stuck.
Okay, let's move on to the action space A. These are the agent's actual choices, the discrete things it can do, which then have to be perfectly translated into commands for those external air cracking tools.
The actions are finite, and they're pretty simple. You have passive monitoring, where it just listens. You have channel hopping, where it tells the Wi-Fi card to jump to a different frequency. And then you have active intervention, which is primarily using authentication attacks.
And the policy is what decides between them.
The policy, P of S, just determines the probability for each of those 3 actions in any given state. The agent is constantly exploring that trade-off. Is the potential reward I can get from a risky attack higher than the safer, steadier option of just listening?
Now for the actual engine of learning, Q-learning. How does this thing determine the value of taking a certain action?
Q-learning is what we call a model-free algorithm. That means it doesn't try to build a perfect map of the world. It doesn't try to learn that P, the transition probability. It just learns by trial and error. The Q value, which we write as Q of S, comma A, is the algorithm's numerical prediction of the long-term goodness, the total future reward if the agent takes action A in state S.
So it's like a gut feeling, but in math form.
It's a heuristic estimate of how good an action is. Exactly.
And the actual learning happens through this temporal difference, or TD, update?
The TD update is the core of its adaptation. It's very simple, really. It just compares the reward the agent expected to get with the reward it actually got, plus the discounted value of whatever state it landed in next. If the actual outcome was better than it thought, the Q value for that action goes up. If it was worse, it goes down. It's just a continuous process of minimizing its own prediction error, and over thousands of tries, it slowly refines its knowledge.
And that whole update process is heavily influenced by those two crucial hyperparameters. Let's start with the learning rate, alpha. This sounds like how willing the agent is to change its mind.
That is a fantastic way to put it. The learning rate, alpha, is a number between 0 and 1, and it dictates how much weight you give to new information versus what you already know. If alpha is high, say 0.8, the agent is very impulsive. It rapidly absorbs the latest experience, and it can quickly forget what it thought it knew.
Which could be good for learning fast.
It leads to faster initial learning, but it often results in an unstable policy. It can thrash around, especially in a noisy environment like a busy Wi-Fi spectrum.
And if alpha is low?
If alpha is low, maybe 0.1, the agent is extremely conservative, it's stubborn, it requires a lot of repeated evidence to change its policy. Learning is much slower, but it's also much more stable and consistent. And for an agent that's operating in this constantly changing environment, finding that balance is the real art.
Then you have the discount factor, gamma. This one seems to shape the agent's whole personality. Is it a long-term planner, or is it a short-term opportunist?
The discount factor, gamma, is fascinating. It's the agent's time horizon. It dictates how much it values future rewards compared to immediate ones. If gamma is very low, close to 0, the agent is a pure opportunist. It's driven by immediate gratification. It only cares about the reward it can get in the next few seconds.
So it'll just go for the easy targets.
It'll rapidly exploit all low-hanging fruit, and it will completely ignore a tough, well-defended network that might give a huge reward but requires long-term monitoring.
And conversely, if gamma is high, close to 1.
That agent is a strategic planner. It's willing to accept small penalties right now, like spending 30 minutes passively monitoring a difficult target, because the massive value of that eventual capture is heavily weighted in its calculation. So tuning gamma is absolutely critical. It's how you manage that strategic trade-off between exploring for new opportunities and exploiting the ones you already know about.
So the reward function itself are the agent's internal definition of success. What's the big prize for Pwnagotchi? What gets it that highest positive reward?
The core motivation, the highest possible positive reward, is only given for capturing a complete and unique WPA or WPA2 four-way handshake. A partial handshake is worthless, and capturing the same one over and over again is not helpful, so the reward is conditional on both the integrity and the uniqueness of the capture.
But it can't just be motivated by that one huge success. You need smaller rewards to keep it going and penalties to stop it from doing dumb things.
Exactly. You have minor positive rewards, which we often call stimulation, and those are given for events that just improve the agent's knowledge of the world. Things like discovering a new access point it's never seen before. This encourages it to look around.
And the penalties, the negative rewards, are critical for steering it away from getting stuck.
Absolutely essential. A penalty is given for excessive stagnation. When that stagnation counter maxes out, that forces it to explore. And crucially, negative rewards are also applied if it keeps trying an aggressive action like a death attack on a target that just isn't responding.
So it doesn't waste its time.
It prevents the agent from wasting time and bandwidth just banging its head against a brick wall. This balance of rewards and penalties is what ensures the policy is robust and not just greedy. It encourages that epsilon greedy strategy where every once in a while it just tries a random action just to see what happens.
Which brings us to the actual mechanics. The RL core is the brain, but it needs a powerful set of external tools to actually carry out its decisions. What specific low-level tools does this Python script depend on to talk to the network?
The Pwnagotchi is really just a sophisticated Python wrapper around the well-established air-cracking tool suite. It uses these tools for everything, from getting the interface ready to injecting the packets. It's a necessary dependency because these tools provide the highly optimized kernel-level drivers you need to do raw 802.11 communication.
Okay, so the first step is always prepping the interface, which is done by AirMona. What special work is that tool doing?
Airmoning is all about making sure the hardware is ready for raw capture. First, it checks the status of the wireless drivers, loads any modules it needs. Second, and this is critical, it finds and kills any conflicting services, things like Hoopa Supplicant or Network Manager.
And normal Wi-Fi managers.
Normal Wi-Fi managers that would try to manage the connection and interfere with the raw access we need. And finally, it puts the card into monitor mode, often creating a new virtual interface, like Wyland Zeromon. Without that tool, the agent is basically deaf and can't do anything.
Once the card is ready to listen, the primary intelligence gathering begins with aerodumping.
Aerodumping is the passive reconnaissance workhorse. It's continuously capturing raw 802.11 frames, and it compiles that real-time table of data, BSDs, ESIDs, client MACsAches, and critically, the RSSI readings that feed right back into the agent's state vector S. Most importantly, it's the tool that actually spots and logs those precious WPA handshakes to the PCIP file.
And we have to say it again. The reliance on aerodumping's text file output is the single biggest structural bottleneck on the Pwnagotchi's performance.
Without a doubt. The need to read and parse that text file instead of, say, accessing a shared memory buffer for that high latency I/O operation on the Pi 0W, and that fundamentally compromises the real-time nature of the agent's perception. It is the engineering constraint that the next generation of these tools has to solve.
And if the RL policy chooses that high-risk, high-reward action of intervention, which tool takes over then?
That would be airplaying. This is the tool for raw packet injection. It executes the action, most notably the deauthentication attack. The agent has to tell airplaying exactly how to build and send these specially crafted management frames.
And the success of that death attack, it relies on exploiting a known weakness in the 802.11 standard itself.
Correct. The 802.11 standard says that management frames, the ones that handle connections and disconnections, have to be unencrypted. And historically, they didn't have strong cryptographic authentication. So airplaying exploits this by spoofing a death frame, making it look like it came from the real access point, telling a client device to disconnect immediately.
But the goal isn't just to disrupt the connection. It's to force a very specific cryptographic event.
Precisely. The death frame forces the client to disconnect. And because clients are programmed to be really aggressive about reconnecting, that reconnection sequence is what initiates the EAPO four-way handshake. And aerodumping is just sitting there silently waiting to capture it. That's the mechanism. That's how the RL agent generates the big reward it needs to learn.
So once the agent is happy, it's archived its PCIP files. Its job is done. But the security team's job, the forensic analysis, is just getting started.
Right. Now we move to the decryption workflow, which is computationally expensive and has to be offloaded. The very first step is always data integrity and verification. We use tools like Pwnagotchi to strip out any junk from the PCP file, but more importantly, to verify the completeness of the handshake.
Okay, what does completeness mean? We always hear about this four-frame requirement, but what's actually being exchanged in those EAPO messages?
The EAP all four-way handshake is the critical exchange that's used to derive the actual encryption key, the PTK, from the password, the PSK.
Okay, so walk us through those four messages.
So message 1 is sent by the access point to the client. It contains a random number, the annonce, and some other info. Message 2 is the crucial response from the client. It contains the client's random number, the S-nonce, and this is where the core math based on the password happens. This message is absolutely critical. If you miss this one, the whole thing fails.
So we have both random numbers now from messages 1 and 2. What's next?
Message 3 comes back from the AP. It includes the group temporal key, the GTK, which is encrypted, and a message integrity code, a MIC. And message 4 is just the final confirmation from the client. But for cracking, we really only need the data from those 4 frames, specifically messages 2 and 3, because they contain the 2 nonces, my MIC addresses, and the MIC. If even one of those is missing, the cracking tools just don't have enough information to even start.
Okay, so once the PCIP file is verified to have all 4 frames, the really heavy work of cracking begins, usually with Hashcat. Why does this have to be done on a separate machine, and what mode is used?
Well, the complexity of WP2 hashing is just orders of magnitude beyond what a little Pi 0 can do. You have to offload it to dedicated hardware, specifically a machine with GPU acceleration. Hashcat is the go-to tool, and it uses mode 22000, which is specialized for this WP-POB PA2 capture format. It just leverages the massive parallel processing power of a modern GPU.
And the speed difference is just, it's mind-boggling.
It really is. A modern CPU might get you, I don't know, tens of thousands of hash guesses a second. A high-end GPU running Hashcat can do billions of guesses per second. And that acceleration means a dictionary attack that might have taken weeks or months on a CPU can now succeed in minutes or hours.
So let's assume Hashcat cracks the password. We now have the plaintext PSK. How does that turn this initial audit into a full-blown forensic exercise?
Now you go to the gold standard, deep packet inspection with Wireshark. Once you know the PSK and the network's SSID, you just plug them into Wireshark's preferences. Wireshark then uses those two inputs to do the same math the client and AP did, and it computationally derives the pairwise master key, the PMK, and then the subsequent encryption key, the PTK, that was established in that handshake you captured.
And once it has the PTK, every single packet you captured, even the encrypted ones, become readable.
Complete forensic visibility. This transforms the whole exercise from a simple password harvest into a comprehensive security assessment. Now, the security engineer can analyze proprietary protocols, look for unencrypted usernames or credentials being sent, assess what the client devices were doing, and really identify the true extent of the breach that happened because of that one weak password.
That is just a staggering technical journey, and it all starts with this tiny learning device. But the project, for all its brilliance, is not without its real-world struggles. Let's move into part 4 and talk about the stability and the technical debt that's facing Pwnagotchi.
Right, the concept is so robust, but the implementation, it really struggles with baseline instability. Because the software is so tightly coupled to specific low-level driver behaviors and Python dependencies, users report persistent issues all the time.
What kind of issues?
Oh, everything. Common driver conflicts with certain Wi-Fi chips, configuration files failing to load correctly, which causes the whole thing to start up wrong. And even worse, sometimes the agent just gets stuck in this loop. The screen just says, looking around, and it effectively halts the entire learning and reconnaissance process.
And that puts us in pretty significant technical debt, especially when you try to integrate modern tech.
Substantial debt. The difficulty is that the original code is so deeply tied to specific older versions of libraries. So developers face this enormous challenge just trying to migrate the core to a modern environment, like fully supporting Python 3 or getting it to audit 5 gigahertz networks. And when new hardware comes out, like the Pi 0 W2, the effort it takes to update all the drivers and kernel modules just shows how fragile that underlying architecture really is.
And that instability and debt, it naturally leads to the community fragmenting. If the main project struggles, dedicated users are going to fork it and fix it themselves.
And we've seen exactly that happen. The rise of these specialized forks, you'll see PyTorch-based versions or ones focused on better hardware support. It's a direct result of that instability. These community efforts, they represent these architectural splits. They often target much more capable hardware, like a Raspberry Pi 4, specifically to get around the Pi Zero's crippling I/O and processing limits. That lets them implement more complex and stable DRL models, like DeepQ networks.
And the limitations of the air-cracking suite, which is so specialized for Wi-Fi, are also pushing modern recon towards broader frameworks. Why is the industry looking at tools like BetterCap now?
Because modern networks are composite environments. An enterprise isn't just Wi-Fi anymore. You've got 802.11, you've got Bluetooth Low Energy sensors, you've got proprietary 2.4 gigahertz radios. Air cracking is fantastic for Wi-Fi auditing, but that specialization limits the agent's overall field of opportunity. BetterCap offers a much broader, unified architecture for this kind of attack simulation.
So what specific advantages does BetterCap give an adaptive agent?
Multi-protocol support, all through one interface. An agent built on BetterCap can seamlessly pivot its reconnaissance. It can do Wi-Fi scanning and death attacks, but it could also start mapping BLE devices or identify IoT fingerprints or even run really esoteric attacks like mouse jacking.
So the future action space, the A and the MDP, it won't just be about Wi-Fi channels.
No, it'll span multiple radio layers. It's about protocol convergence. The agent will be optimizing its mission across multiple protocols at the same time.
And the developers have explicitly recognized this by starting to integrate DRL with BetterCap.
It's the essential next step. If you instrument BetterCap, the agent could potentially decide to, say, ignore a heavily defended Wi-Fi network for a while and instead focus on exploiting a vulnerable BLE protocol it just found nearby because its math tells it that action offers a higher expected reward. That kind of holistic assessment is only possible with a unified framework.
And we have to talk about WPA3. The entire premise of capturing a four-way handshake is basically obsolete with the new standard. How does that force the agent to adapt what it's looking for?
The traditional four-way handshake is completely incompatible with WPA3 Personal, which uses something called simultaneous authentication of equals, or SAE, and that protocol just eliminates the weak handshake structure that the whole password cracking attack relied on. So future adaptive agents have to completely abandon the search for that four-frame exchange.
So what's the replacement target? What do they look for instead?
They have to prioritize capturing PMKIDs, pairwise master key identifiers. The PMKID is generated earlier in the connection process, and critically, it can be captured from a single EAPOL frame that's exchanged between the client and the AP during negotiation. You often don't even need an active death attack.
And tools like BetterCap already support that.
They do. It's a faster, clientless vector, and adapting to hunt for PMKIs is absolutely vital for any adaptive agent that wants to stay relevant.
Okay, let's address the most complex part of this whole system, the legal and ethical tightrope walk. Pwnagotchi is an autonomous agent. It's just maximizing a reward function, and that optimization can lead the user directly into very serious legal trouble.
This is the absolute crux of the autonomy liability paradox. The legal framework here is crystal clear. Passive listening might be a gray area, but it's dramatically different from active interference. The moment that RL agent autonomously decides to execute a deauthentication attack using airplaying, it crosses a bright red legal line.
Under U.S. law, what specific statutes is it violating with that active packet injection?
In the U.S., unauthorized network interference falls right under the Computer Fraud and Abuse Act, the CFAA, specifically the part about access without authorization. But more critically, the act of intentionally intercepting private electronic communications, even if you do the cracking later, that risks falling under the Federal Wiretap Act, which has very heavy penalties.
And the intent is inferred from the action.
It is. You generated traffic, the death, specifically to facilitate an interception, the handshake capture.
And in the UK?
In the UK, the agent's active interference impairing the network's operation with spoofed frames, that lines up with Section 3 of the Computer Misuse Act of 1990. But regardless of the jurisdiction, the person who deploys the tool is legally responsible for what that tool does.
And this is where the AI part is so tricky. The user didn't manually type the death command. The RL agent chose that action because its internal math decided it was the best way to maximize the reward function that the user set up.
And that is the paradox. The user initiates the agent. The user defines success by writing the reward function. The agent then autonomously finds the best way to achieve that success, which often requires illegal interference. And since the user intentionally activated an agent that was designed to do this, the user assumes full liability. This is why you see a lot of ethical security researchers, when they're outside of a very formal, defined scope of work, they just disable the active injection capability.
Right, which highlights the inherent legal conflict in these autonomous adversarial systems.
It does.
But the innovation in these offensive tools, it has to be met with defensive innovation. If the attacker is automating, how does the defender adapt?
The most effective first defense is always protocol hardening. Just migrate all your networks from WPA2 PSK to WPA3 Personal. By using SAE, organizations completely neutralize the agent's main attack vector. The agent can capture all the WPA3 traffic it wants, but without that exploitable handshake structure, the offline cracking attack is just dead in the water.
And beyond just hardening the protocol, how do we actively detect that an optimizing agent is even there?
For active defense, you need robust network detection and response, NDR, or a modern IDS. Since the agent's intervention creates these recognizable, predictable anomalies in the 802.1 management frames, your defensive systems have to be tuned to look for them.
What kind of patterns are you looking for?
You're looking for unusual patterns. Sudden, high-volume bursts of deauthentication frames, especially if they're using spoot and MASI addresses. Or sequences of really rapid death and reuse events that just don't look like normal client behavior. Detecting that coordinated high-frequency activity is how you flag an active recon attempt.
And given how portable this device is, you have to think about physical security, especially with the threat of drones.
Absolutely. The rise of these cheap commodity radio devices means an attacker doesn't need physical access anymore. So organizations have to think about limiting signal propagation. This means using specialized architectural materials like shielding paint or foil and making sure your AP placement limits how much signal bleeds outside the building. That's how you counter the threat of a remote actor using an autonomous device on a drone to do war driving without ever setting foot on your property.
So as we wrap up and synthesize Pwnagotchi's legacy, what's its ultimate contribution to the field of adaptive security testing?
I think Pwnagotchi is a seminal proof of concept. Its greatest contribution was validating that effective, continuously optimizing, autonomous adversarial agents can run successfully on dirt-cheap hardware. It did that by framing reconnaissance as a solvable MDP. It forced the entire security community to admit that AI-guided attacks don't require supercomputers.
And its limitations are now the roadmap for the future.
Exactly. The system's limitations, that I/O latency bottleneck, the technical debt, the legal mess of autonomy, those are now the critical architectural challenges that are defining the next generation of these security systems.
Looking ahead, where do we see the most exciting leaps in this ML-guided attack automation? You mentioned geospatial policy optimization.
This is where we move the RL framework beyond just the digital world and into the physical world. Future agents will integrate GPS metadata, which tools like Aircrack can already log, and they'll feed that directly into the state vector S. This will allow the agent to learn complex, optimal physical movement patterns.
So the policy won't just choose a Wi-Fi channel, it'll choose a physical direction. Go 3 blocks west.
Exactly. It's automating the literal route of war driving. The agent will learn which routes, which neighborhoods, which side of a specific building gives it the highest sustained capture rate. It will fully optimize the real-world physical path of the reconnaissance mission.
And that level of complexity, that's going to demand a major hardware upgrade to support the AI models you'd need.
It does. The simple Q-learning that runs on the Pi Zero is not enough for these high-dimensional state spaces that include things like GPS data. So the shift to more powerful hardware like the Pi Zero W2 and the Pi 4, it's inevitable. This scaling is what will support the more advanced DRL models, things like deep Q networks or PPO that you need for stable learning in these complex environments, and for auditing new standards on the 5 and 6 gigahertz spectrums.
Which brings us to our final thought. We spent this entire deep dive talking about how an AI can learn to optimize its attacks against a network. But what happens if we just flip that concept on its head?
Well, the exact same principles of machine learning how to optimally interact with a dynamic environment can and absolutely must be leveraged to create autonomous defensive agents. These systems would use the same continuous traffic monitoring and machine learning core, but not for simple signature-based detection. They'd use it to predict the optimal counteraction to a threat as it's emerging.
So if the attacking agent is constantly adapting its policy to get the most reward, shouldn't the defender be constantly adapting its security posture to have the minimum risk?
Absolutely. These autonomous defensive systems could automatically reconfigure a software-defined network and SDN in real time. If the system detects a Pwnagotchi-like agent starting death attacks, the defensive AI could instantly segment those targeted clients, or it could cloak the access point, or automatically shift the frequency away from the attacker. That dynamic adaptive mitigation, that is the necessary defensive parallel to the offensive innovation that Pwnagotchi represents. It's the next frontier in network security, and it's something well worth exploring further.